Yo, what's up, guys? Yo, yo, yo. Am I live? I think I am. Yo, everyone. What's up, boys? I think we're gonna be live at. No, we are live, actually. We are live. Of course, we are. Server-side vulnerabilities. I think I have already documented my stat. This guy. Just kills rails. For the session. Pasta. Right. Oh my! Wow, voice meter VTune map. VTune. Voice meter sound recorders. Downloads. Desktop. Us? Guys, we're. Oh, it's on this laptop, I think. So, yeah. Oh my god. Yes. Yes, 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 yes. 1, 1, 1, 2, 1, 3, 1, 3, 4, 1, 4. So, yo, hello, guys. Hello. Hello, everyone. What's up? How we doing? How are we doing, guys? How are we doing? Yep. Introduction, contents. Yeah. I have a note of 1, 1, 1, 2, 1, 3, 1, 4 as well. Example network. I don't have I have um I think I have example networks. Yes. Oh no, I haven't wrote it. I didn't wrote it. I didn't wrote the example network notes. Charts only for analytics. Docs. What's in the docs? Have some mathematics here. To class. Talking devices, running functions, then the cloud. What's the question mark? Well, yeah. Within each pair of adjacent layers, what are the nodes exactly? Yeah, what are the nodes? Let's see, nodes. The very first, yeah, it was in the 1.3, yeah, 1.13, yep, 1.13, yep. For social issues, network hardware, have done that as well. Network software, yep. What was the network software exactly? Yep. So the subnets. I forgot all of these. Holy shit. I've stopped at the 1.5 example networks, the internet. I haven't documented this anymore. Um, I know outline of the rest of the book. We yeah. Let me open the stream again. No one. No one. I guess no one. Uh, so guys, I decided that I will be learning networks from this book. We are gonna be also learning this book, the code, the hidden language of computer hardware and software. I think this is like really good book for the beginners. Bytes and hex and assemblage of memory, automation from APASI to chips to classic microprocessors. Yep, I'm gonna be learning this book as well. But there is this thing that I still have to think about the ways how I can combine it with the streaming, because I don't want to be sitting here and like showing you, yeah, I'm learning this, I'm like reading this one. I'm also found this really cool website that I will be, this is flashcards, and you can, you see like some of them have German communication dictionary. This is the network's intro. I'll be gonna be making the flashcards about this. Actually, uh, we can do it for today. I think so. Yeah, I think we can make the flashcards for today. That might be our stream. Let's consider it because I have the notes right. Um, can Gmail myself. Can Gmail myself right now. Wait a minute. Or I can actually upload it on Drive. New file upload. Yeah. Let's see it on this PC. No, desktop. Yeah. Hmm. I'm gonna be getting all of that. We're gonna be making networks intro. I'm not gonna be like dividing. I'm just gonna be making it for the chapters. And right thing is that every day I'm gonna be reading the sum of these, right? Guys, it takes so much time, guys. You don't even understand. You don't even understand, guys. It's so hard. Takes so much time, but I'm gonna figure it out eventually. So yeah, um, I'm gonna be doing this every stream. Every stream, I wanna do flashcards. I wanna do the practice. There is this learning path. That's server-side vulnerabilities. One of three. Um, I think it as long as I know the answers, it's quite easy to make for to answer the flashcards, you know. But I don't have labs, you know. When I want like I can like postpone my stream. Can be like streaming later, or I can be streaming like earlier, like this, like at 6. Can be streaming at 6. Um, Eventually, you know, I have to divide, right? Stream time and learning time. I have to learn the networks. I have to learn the code, like 1 hour, like minimum each, or I just have to like focus on one. Uh, I think, I think maybe like we're gonna focus on this book first. I don't know. Yeah, this is Bayern's the recent ones. Yeah, there's a note intro, hardware question, networks, yeah, reference models. Yep. What's that? Oh, this is in 134. What's that? Oh, this is network software. This is network software. So network software, yeah, on the client machine and the server machine. Yeah, that's client server interaction. Mm-hmm. Mm-hmm. Uh, I think that my notes are pretty good and detailed. I don't exactly know, but I think they are. Where's that hacking fundamentals for sheet? Renode. Okay. Gonna be these. We're gonna be learning this as well. I wanna learn this as well because I think it includes labs as well, right? I wanna doing like hands-on as well. That's why. Or I can just forget about it. I don't know. Like, let's see. Lab. Yes, there's lab. I can do it. Like, there's lab. One lab, two. Yep, lab. Web shall upload your content type restriction bypass. Lab basic answer against another backend system. Labs, the username enumeration with different responses to if a simple bypass. What's the old? User ID controlled by request parameter with password disclosure and the file traversal simple case. Yeah, this is I mean the easy one, right? Again, we have to see how much time it takes to do this to actually do this on stream, right? So it won't be. I don't want this, right? Don't want that. This is for the flashcards. This thing. What else can you do? Okay, we're gonna download this first. Yep, we are gonna be getting that. I don't want this anymore, and this is gonna be our main forte. So, what I noticed that like in the first introduction part, the only like challenging stuff was this stuff, you know, So yeah, one thing as well, we can do the problems. We can do the problems. You know, when you have trained your brain to carry a box of 3 8 mm tapes instead of a flask or instead of a flask of brandy. Yeah, and I forgot this actually, guys. And we are learning it in the metric units. I think so. I think so. Who is who in the yeah? Who is who? Who's who? Who's who? Let's understand. Who's who? Yeah, sensors, stuff like that, wireless. Yeah, it's in the matrix. So we are gonna be starting from 1.6 or no? Wait a minute, let me see. PIP de facto de jure for bylaws in certain standards and stuff like that. I also have to buy these. A subscription, yeah. We have to subscribe to this. Yeah, I'm gonna make a quick payment, guys. Let me black screen. Holy. Make sure that you won't see anything. Anything. Because I'm limiting to the flashcards, you know? That's why I want to make these. It's annual, of course, like 25 annually. Holy. Oh. No, you won't see, right? Yeah, you don't see anything. Don't see shit. Okay, no thanks. What? Yeah, it was 25, but I don't know. I still got charged 30. I don't know why. April 2027. Okay, let's go. Let's go. Let's fucking go. The isn't the only place to consume education content and create deep linked space repetition flashcards and deep linked nodes. Deep linked nodes. Browser extension enabling you to create these flashcards and nodes deep linked and space content on web pages and time codes in YouTube, Coursera, and the Udemy videos. Let me go through that.
The Smarter Humans Web Clipper browser extension enables you to create AI-generated flashcards and summary notes that are deep linked to the exact location in online content. The extension is compatible with Chromium-based browsers, including Chrome, Edge, Brave, Arc, and Opera. Add the extension to your browser by clicking your profile photo or avatar and then selecting Integrations. Click the puzzle piece-shaped extensions icon and pin our extension to the browser's extensions toolbar. Then you can easily activate it on any web page or online video when you need to use it. The extension enables you to create AI-generated flashcards and notes that are deep linked to the exact location on a web page or time in a video. This allows you to return to the precise location in the source where you learned something. Ordinary linking would take you back to the top of the web page or the beginning of the video, but deep linking will
Oh.
take you directly to the exact spot on the web page or the specific time in the video. Now let's look at some more examples. I'll create flashcards from this Wikipedia page. First, I'll select some text. Then, I'll utilize the AI generation feature to create a deep linked flashcard. Please note that we also offer the option to create a manual flashcard, which automatically pastes the selected text into the question and answer fields, allowing you to edit it before saving.
What?
Now watch me create a flashcard using the screenshot tool. We don't have AI generation for this tool yet, but we'll have it soon enough. The screenshot will be pasted into the question and answer fields. You
Okay.
can edit the flashcard here, and it will be deep linked to the region of the screenshot. A favorite option here is to turn that screenshot into a redaction flashcard where you cover over areas of interest, such as labels on an image or cells in a table. When you practice memory retrieval, you'll have to recall what's behind each redaction before you click to reveal it. Creating a note works similarly.
Oh.
Watch for a few seconds as I demonstrate this. Our full-page actions are very useful. First, you can save the web page as a PDF to your account's library and then read and process it later. Next, you can generate a set of AI flashcards. The extension begins at the top of the page and works its way downward. Each flashcard will be deep linked to the relevant passage in the text that explains the answer. Our large language model prompt aims to ensure that there is a flashcard for every important teaching point. Because of this, you may have to click the Generate More button several times to cover the entire page. We recommend curating the flashcards you want to keep in your account and proofreading each one to ensure accuracy. The AI summary note processes the entire web page in one click and provides a comprehensive list of the key teaching points. When you save it, it will be placed in the Web Clipper inbox within the Notes section of the app. The extension enables you to create deep linked flashcards and notes while watching videos on YouTube, Coursera, and Udemy. Let's look at how this works on YouTube. Creating a deep linked flashcard or note is analogous to the process on a web page, except that the link is to a specific time code in the video. The additional video actions include saving the YouTube video to your library, where you can watch it later and create linked flashcards and notes. You can generate sets of AI flashcards starting at the beginning of the video, and we'll process 5 minutes of the transcript. With each click of the Generate More button, additional flashcard sets will be created in blocks of 5 minutes further into the video. An AI summary note will process the entire video transcript and create a list of the key teaching points. Here are a few final housekeeping options. If you click your photo, you can log out or set your language preference for the AI. If auto detect is unchecked, then the flashcards will be written in your chosen language, regardless of the language of the video or web page. If the extension ever gets in your way, you can click this arrow to stow it on the side. If you need further information about the Web Clipper extension, just click this help question mark. We are actively working on numerous enhancements outlined in our roadmap. We welcome feedback, and you can reach our CEO directly at david@smarterhumans.ai.
Okay. So let's fucking do it, man. Let's fucking integrate it to Chrome. What's that? I don't know what's this token. Readwise. What's this? Got it. To Chrome. What's a Readwise? Readwise. Is this like you purchase the books and stuff like that? Or it's for their books and stuff like that? Okay. So let me import materials. Downloads. Desktop downloads, right? Yes. What? What? Is that, oh, they are MD files. Properties. Open with. So with open with. Some more options. Not rar. Send to. Copy space. Give access scan. Editing notepad. Ubiquitous computing was EPTV, peer-to-peer, person-to-person, person-to-server, hotspot based on the cookies. Does it look like that in my sheet? Man, this is crazy. This is crazy. This is not how I made that. Oh my god. Network software. I think I have to make. Oh no, no. No, this is nice. Network software, I'll open now and open. You see? What's this? Service example. Stream, sequence of pages. Movie download. Reliable by stream. Connection oriented. Reliable by stream and movie down allows movie download. Unreliable connection voice over IP. Service primitives. Connection oriented versus connectionless service. Design issues for the layers. Yeah. Mm. So file. Save as. No, txt, man. Desktop. Save. Save as markdown to keep formatting. See, it's a text file. To keep the kind format like bolding and heading, save markdown file. If you save as a print, all format, okay, cancel. Yeah, but how do I upload it then? It's an MD files. Question mark. Let's ask chat that. Okay. Let me stop right here, right at this moment. You know, um, what the fuck is happening? Oh, I think I lagged. I think I lagged. Oh, so I'm sorry, guys. I'm so sorry, guys. My like that. Yeah, it's really hard. It's really hard to stream this. Can I use like copy text or something like that to drag your study materials here? Docs, PPT, PDF, images, etc. Hmm. So does it work here? Login. Online PDF version. You can only save the PDF to the library. Oh, and I can work it there. Okay. It's already saved in the library. I can just pin it, right? Yeah. Don't know what to do. I'm kind of lost. You know, production metrics, CK units. To avoid any convenience, source saying that this process is okay. I also need how we go in touch. Uh, I need this. Not exactly, but works. Let me get the note. We got what we need. We got what we need. So it's always here. So I wanted to do this. Like go into this stuff in the metric stuff. What's the hell divers, man? Images. Oh, it's nice. Not bad. I want to go through these like metric units to everything. Okay, the principal metrics prefixes are listed in figure 1.39. The prefixes are typically abbreviated by the first letters, with the units greater than 1 capitalized. Wait. So kilobytes, megabytes, these are capitalized. All right. In kbps for kilobyte seconds, thus for kilobytes. Okay. Thus one megabytes communication line transmits 10.6 bits a second. Okay. And 100 psec p. This one or this 100 ps. PS. No. Every 10 minutes 10. What? So metric prefixes. So what's the milliseconds then? 0.001. So second or what? Kilobytes per second. MB. Okay, kilometers rather than okay. Often on the okay, much smaller than the what? Internetworks. Was this, yeah. Now, for measuring memory, disk file, and data byte size in its common structures, the units have slightly different meanings. There, kilo means 210, 124, rather than 10,000 to 10. Just 10,3. Okay, because memories are always a power of 2. Yeah, because of the bytes. They're like saved in bytes. Thus 1 kilobyte of memory contains 124 bytes, not 100,000 bytes. Note also that capital B is that usage to mean bytes, units of 8 bits. Capital B is that usage to mean bytes. So wait a minute, let me type it. I don't understand the kilobyte byte. So there, it's not kilobits, it's kilobytes. So 1 kilobyte is 8 kilobits. Bits. Similarly, 1 megabyte memory contains 220 megabyte. 220. If it was like 100 was a 210, it's 220. Yeah. Bytes times 10 bits. Okay. A kilobyte per second communication line transmits 1000 bits per second, and a 10 megabytes line runs at. Okay. Communication line speeds. Let me see. Okay. So 1 kilo, 1 kilobits per second, right? Per second transmits how much? We have to learn this. We have to learn this. This, I think, this is like really important, right? In stuff like that. For example, if we program the machines that transmits more, we can kind of break it. No, what do you think? Or maybe if we transfer something that is like really, really, really small, we can maybe potentially sneak in. What do you think? Ooh. However, 1 kilobyte transmits 100,000 bits. Bits. LAN times 1000. No, something's wrong now. Oh, it's 10. So yeah. If 1 kilobits per second line transmits 1000 bits, 1 megabyte, 1 MBS will transfer 1000 times 1000, right? Because there is 1000 bits in 1 megabyte. So million bits. So eventually 10 MBC will transfer times 10, which is 7 zeros. Yeah. Yeah. Bits. This is what lines transfer, right? This is what lines transfer. Lines transfer. But in memory, yeah, it can hold the bytes. It's holding bytes in memory. Memory, 1 kilobyte is bytes, which is therefore 124 calculator times 8, right? Is bit. Bit. Hmm? But there was some kind of thing, right? The pages are typically abbreviated by their first letters with a unit greater than 1 capitalized. One exception. For historical reasons, in kilobytes per second, 4 kilobytes, yeah, kilobytes per second. Wait. 1 Mbps conversion transmits bits, yeah, sure. PSEC. Wait, 100 PSEC or 100 PCs. Clock ticks every 10 minus 10 seconds because pico, like pico is minus 10 minus 12, and times 10 is times 100 is 10 minus 10. Okay, ticks. Million micro mean. ITSEC was. So there's milliseconds, microseconds, nanoseconds, picoseconds, femtoseconds, attoseconds, zepto, yoctoseconds. Kilosecond, mega, giga, tera, peta, hexa, zeta, iota. But no, 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 no. There's 1 second, right? There's 1 second. Yeah. 1 megabyte, 1 kilobyte. Wait. Was it like 210? 2 bit shift? Wait. What the fuck? Oh, I'm not a programmer, I'm standard calc. Holy shit. Holy shit. Scientific. 2 times 10. 124, yeah. So this is 210. MB is 220. 1 GB 230, and 1 TB is 240 in seconds. 1 second is 1 second. What? 1 millisecond, 1 ms equals 10 minus 3 seconds. 1 microseconds. So you kind of 10 minus 6 seconds. Yeah, but I don't know how to work with modern calculators, guys. Like, it's hard. And I also forgot, like, operations are so dumb, man. Nanoseconds, 10 minus 9. Yeah, okay. However, a 1 kilobyte per second communication line transmits 1000 bits per second. Yeah. If I have to prove it. Like, guys, if still there is 1,000 beats in second, in millisecond will be 1, right? If 1,000 bits are transferred in 1 second, how many are transferred in ms? 1. 1. Mm-hmm. Mm, mm, mm. The reflection and interface. Okay, shut up. Okay. To avoid ambiguity in this book, we will use the symbols KB, MB, GB, and terabyte for 210, 220, 230, and 240 bytes. So, what do we mean by that? Okay, I think I understood. And the symbols, KBBs, MB, GBs, okay, bit sec, respectively. For 10.3, 10.6, 10.9, 10.12 bits per second. So 1,000 bits per second, a million bits per second, yeah, milliard, billion bits, yeah, you know. Mm-hmm. Gigabytes per second. Bits. Okay. Outline of the rest of the book. Summary. Okay, let's try some. Imagine that you have trained your Bernie to carry a box of 3 8mm tapes instead of a flask of brandy. Okay, he carries 3 8mm tapes. What's tape, by the way? The tape is image, yeah. Oh, he carries 3 of these. Okay. When your disk fills up, our disk fills up, you consider that an emergency. Flask of brandy. What? Come on, man. Oh, he carries that. Okay. These tapes each contain 7 gigabytes. Okay, we have. So we have in total. Come on, man. 21 GBs. 21 GBs. That's 240, right? 230. 230 bytes. 230 bytes. Okay. Um, the dog can travel to your side wherever you may be. So wherever are we, the dog can travel 8 kilometers hour. Okay. 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 So 150 MBs, right? MB seconds. MB seconds. MB per second. That is 150 150 times 10 3. No, 10-6. 10-6. 10-9. It's 10-6, right? It's 10-6. Yeah, 10-6. Right. It's 10-6. Beats per second. Okay. Higher data rate. So it transfers data for what range of instances does Bernie have a higher data rate than the transmission line whose data rate excluding overhead? Well, I don't understand what this means. Excluding overhead is 100. Okay. So does it thing change at like 8 mm tapes instead of flash of brandy? So this line transmission line we transfer our 27 bytes. So 230, right? Hmm. 230 bytes is 230 bytes like times 8, which is 230 times 3, which is 233. 233. We have 233 bits in total. So my question is, where I have to divide? I don't know, man. Come on, man. So 233 in power divided by 150 times 10^6. I don't know why I'm doing this, but in 1 second, man. Oh, wait. I shouldn't be doing this first. So the drug travels like 80 kilometers an hour, right? Yeah. Uh, kilometers hour. So if we are gonna position ourselves at 18 kilometers, it's gonna arrive in an hour, right? Can travel to your side wherever you may be at 18. For what range of distances does Bernie have a higher data rate than a transmission line whose data rate? So, so in 1 hour, it's gonna deliver more. It's gonna deliver more, right? I know. I mean, I know. I understand, but I can't figure it out, man. Let's see. Let's see. I need to understand. Let's see. Get help. Yeah, 21 gigabytes times 8 gigabits. Yep. Benny's speed is 5 milliseconds. I was doing that. Benny's data, great formula. If distance d matters, time equals d over 5. So data rate is the amount of data over time. Thousand meters per 60 seconds. If you go 1000 meters per hour, means 60 seconds. In 1 second, it won't. In 1 hour, no minutes, man. Fuck yeah. Yeah, any d meters for like it covers any d meters. Yeah, d meters. Time is meters. Like no. T over 5. Why? Yeah, I mean the speed equals time times distance, right? Time equals speed over distance. No, speed over distance. No. Am I stupid? Am I stupid? Fucking speed is time times distance. No? Oh my god. Distance equals speed equals distance over time? Oh my god, I'm so stupid, guys. I am so stupid. I am so stupid. I am so stupid. Speed equals, oh my god, equals distance over time. I am so dumb. And time equals distance over speed. S. Yeah, speed. Yeah. And for any distance, our dog's the time would be like distance over 5. Yeah, e over 5. That's right. And the rate is the amount over time. The rate is the amount over time. Rate is amount over time. So it is 21 GBs. It was like times, yeah, 808 gigabits. Yes, 168 gigabits. And that's 10.9. Yeah, bits are 10.9. Bits are like 10.3. I mean, yeah, 10.3, 10.6, 10.9, and bytes are 2.8 to, yeah. Mhm. So supposedly, I think we always go to bits, not bytes. No bits, huh? Gigabits. Wait, I mean, it's same sheet, no? 2 in power of 33 is something like this, and 10 in power of 9 times 168. No, it's not the same. Actually, not the same. Right, what? So there are. Come on, man. Come on, guys. Help me. That's why I need help, man. There are gigabytes, right? Which are 23 bytes. It's literally written here, man. 1 GB memory contains 230 230 times 21 bytes times 8, this, right? was 21 gigabytes. So what he did, 21 gigabytes. So he is doing here, like gigabits. This is gigabytes. They are, yeah, gigabits. And then he multiplies 10 9. What? What? So wait, let me ask you. There are 21 GBs, gigabyte of memory. Gigabytes of memory. Yes, exactly. Yes. Wait. Stop. 21 gigabytes of memory equals 21 times 230 bytes. No, in many contexts. What do you mean in many contexts? Memory RAM, low level computing. In memory RAM, operating on low level computing 1 GB actually, yeah. Decimal used in networking and telecom. Used in network speed, maybe GPs, many sort of manufacturers, 1 GB equals. So I need it. But wait. I don't understand where am I wrong, guys. You know, I shouldn't be wrong, no? So let's go here. Measuring memory, disk, and file and database sizes in common industry practice, as the units have slightly different meanings. There, kilo means 220, 210, rather than 10.3. Measuring memory, okay, because memories are always a power of 2. Thus, 1 kilobyte of memory contains 124 bytes, which is therefore 1 byte is 8 bits times 8. No? Yes, I think so. No? Not 1000 bytes. Note also the capital B in that usage to mean bytes, units of 8 bits. It means bits, yeah. Similarly, 1 megabyte of memory contains 220 bytes. Yeah, 1 gigabyte memory contains 230 bytes. Okay. However, a 1 kilobyte per second communication line transmits 1000 bits per second, and 10 megabyte line. Okay, powers of 2. Unfortunately, many people tend to mix up these two systems, especially for disk sizes. To avoid ambiguity, in this book we will use the symbols KB, MB, GB, TB for 210, 220, 230, 230 bytes. And the symbols KBBs, MBs, GBPs, and TBPs are like bit seconds respectively. Okay, 7 gigabytes. What does it mean? 7, 230 bytes. No, 7 times 230 bytes. Tannenbaum on problem solutions. And it's gonna be fucking pricey. Hoo-hoo. What's that? Yeah, it's same here. The dock can carry 28 gigabytes, which is 168 gigabits. A speed of equals kilometers second. 5 meters x. The time to travel distance x kilometer is x over. Okay. 200x second, yielding the data rate of 168 over 200x GBPs. Or these MBPs. My eyes hurt. It's explained in the same way. There are 20 gigabytes of memory that should be transferred over the line. Okay, we are just gonna remember it, right? We are just gonna remember it. An alternative to a LAN is simply a big time-sharing system with terminals for all the users. Give to another a client server system using LAN. The LAN model can be grown incrementally. If the LAN is just a long cable, it cannot be brought down by a single failure. If the servers are replicated, it is probably cheaper. It provides more computing power and better interactive interfaces. Okay. The performance of a client-server system is strongly influenced by two major network characteristics: the bandwidth of the network, that is how many bits second it can transport, and the latency, this is how many seconds it takes for the first bit to get from the client to the server. I'll give an example of a network that exhibits a high bandwidth but also high latency. Then give an example of one that has both low bandwidth and low latency. Okay. So high bandwidth can transfer many, but it reaches time to get there, right? So long distance, yeah. So it seems explaining here. A transcontinental fiber link might have many gigabit second of bandwidth, but latency will also be high due to the speed. But the latency will also be high due to the speed of light propagation. Yeah, this the speed of light what's that? The constant defined exactly as meters per second. Okay. Let's see. Let's ask GPT. Let's ask GPT. Doesn't mean low latency, okay? Now let's break it down clearly. What is being said? A transcontinental fiber link can carry huge amounts of data per second, yes, but has a noticeable delay. Why latency is high? Because of the speed of light limit. Light in fiber travels at about in fiber. Yeah, 2 or 3 of speed of light in vacuum. It's okay. So, 5,000 kilometers across a continent. If the time is 5. Wait. What? Time equals distance over speed. 1,000 kilometers. Okay, and this meters. Light in fiber travels at about. Okay, it's so constant, right? The speed of light in vacuum is a fundamental physical constant. Exactly, okay, per second. 3, okay, what did this guy say? 2.8. 2 times, yeah, okay. Water light travels at of its vacuum speed in the water in the glass. Okay, same as no, not same. No, not it's not same, but it's same. Glass in the glass, it's same. In the fiber. Mm-hmm. Mm-hmm. Okay. Besides bandwidth and latency, what other parameter is needed to give a good characterization of the quality of service ordered by entity used for digitalized voice traffic? Voice over IP, video traffic, and financial transaction traffic. Speed, latency, and security. Like encryption. Encryption? A uniform delivery time. So the amount of jitter in the network is important. This could be expressed as the standard deviation of the delivery time. Security is for security reasons. So the jitter is for the security reasons. So this should be said as a standard deviation of the delivery time. So it won't. There's always a deviation. Okay. A factor in the delay of a store and forward packet switching system is how long it takes to store and forward the packet through a switch. If switching time is 10 USEC, it is this likely to be a major factor in the response of a client system as a client? As you know what I'm saying? I think that we shouldn't be studying these things because we don't know like switches. What's switching time? Like we don't know much. A factor in the delay of a store and forward packet switching. Let's go again. Yeah. Round trip. Okay. Type of delay for one way delays. Okay. MS. This is 0.1 ms. So we always go down to MSs or MSs, right? Or registers and cache work on nanoseconds. So if we divide the distance over speed, we get time it takes, which is a delay, right? No, I mean distance over speed, we get time, which is the delay. Delay. Okay. Let me figure it out. The sixth one. Client-server system. So client-server system uses a satellite network with a satellite at a height of 40 kilometers. Okay, we have to the best case delay in response to a request. So what's the speed? I would divide this 40. I would divide this 4,000 over some speed, right? The request has to go up and down. So I have to understand this. So where was that? It actually was right here. No connection oriented request reply. Yeah, I accept response, request for data, reply. This is no, we have to connect for the request. Gives okay, give me the request. Okay, I'll give you. Okay, so sends it and okay returns. So it's 4. Okay, so 160,000 kilometers over what? Kilometers over kilometers per second equals. Fuck. Is it like well good? Ah. Mm. And delete this as well. It's 15. It's 8. 8 over 15. Was seconds. These times what? Wait, what was the answer? What was the answer? About, yeah, about. It's about. 600 sec. Yeah, it is 600 sec. That's right. So, and the milliseconds, the time 10 minus 3, right? Or like times 1000 milliseconds. Times 1000 milliseconds. So I have to try to like always go to milliseconds. You're right. Okay. In the future, when everyone has a home terminal connected to a computer network, instant public referendums or notified legislators will become possible. Ultimately, existing legislators could be eliminated. To let the will of the people be expressed directly, the positive aspects of such a direct democracy are fairly obvious. Discuss some of the negative aspects. 7. There is always no single correct answer here, but the following points seem relevant. The present system has a great deal of inertia, checks and balances built into it. The inertia may serve to keep the legal, economic, and terms from being turned upside down every time a different party comes to power. Also, many people hold strong opinions and controversial social issues without really knowing the facts of the matter. Allowing poorly reasoned opinions to be written into law may be undesirable. The potential effects of advertising campaigns by special interest groups of one kind or another have also to be considered. As the major issue is security, a lot of people might worry about Some 14-year kid hacking the system and falsifying the results. Okay. 5 routers are to be connected in a point-to-point subnet. Between each pair of routers, the designers may put a high-speed line, a medium-speed line, a low-speed line, or no line. Okay. If it takes 100 milliseconds of computer time, what milliseconds, to generate and inspect each topology, how long it will take to inspect all of them? What? What's that? May put a high speed, medium, low, or no. Yeah. Or no line at all, if it takes. And let's see the answer. Call the routers ABCD. There are 10 potential lines, okay? Each of these has 4 possibilities, 3 speeds or no line. So the total number of topologies is 410. Here's the topologies. Topology. What's a topology, man? What is topology? Networking? Layout, logical topology. How data actually flows may differ from physical layout. Common network topologies. Bus topology. All devices share a single cable. Pros, simple, cheap. Cons, with cable phase, entire network phase. Star topology, most common today. All devices connect to a central switch router. Okay. To manage on one failure doesn't kill entire network. Cons, central device equals single point of failure. Okay. Ring topology, device from a closed loop. Okay. Mesh. Devices connect to many or all others. Pros, very reliable, redundant passes. Cons, expensive, complex. 3. Hierarchical, combination of star and bus, such like hierarchy. Provide networks internet backbone. Was the mentioned hierarchical. Okay. So we have 1, 2, 3, 4, 5, 6, 7, 8. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. The 10 possibilities. 4 times 10. Yeah. 410. This guy, 100 milliseconds each, it takes seconds. So inspecting, why am I inspecting them? I understand that, like how many topologies are there, and I understood how many topologies it takes for computer to generate and inspect each topology. How long it will take to inspect all of them? Divided by 100. Yeah, all of topology divided by 100. That's that many seconds. Milliseconds. Yeah, that's true. That's true. Yeah, because 100 ms is 100 times 10 in power minus 3, which is 0.1 second. And this guy times 0.1 is like the comma before 6, and it's the same second. more than 29 hours to inspect them all. Okay. This kind of a broadcast subnet is the capacity wasted when multiple hosts attempt to access the channel at the same time. As a simplistic example, suppose that the time is divided into discrete slots, with each of the n hosts attempting to use the channel with the probability p during each slot. What a fraction of the slots will be wasted due to collisions? I feel like I have not studied this. What's in the summary? Personal area networks, local area networks, metropolitan area networks. What's the fucking broadcast, man? If I search broadcast, look, it's gonna be mentioned like million times. Network hardware, it's in the network hardware, protocol hierarchies. Yeah, let's go. A disadvantage of a broadcast subnet. A disadvantage of a broadcast subnet is the capacity wasted. To access the channel at the same time. I have also done this actually, guys. I have also done this actually, but I don't remember. So subnet is the capacity wasted when multiple hosts attempt to access the channel at the same time. As a simplistic example, suppose that the time is divided into discrete slots. When multiple hosts attempt to access the channel at the same time. As a simplistic example, suppose that the time is divided into discrete slots. I have to do this or that one. We model one time slot. Each of the n hosts transmits with the probability p. Let x number of hosts transmit in a slot. NP binomial. Collision happens when x. Okay. Wait a minute. I have to understand. A disadvantage of a broadcast subnet is the capacity wasted when multiple hosts attempt to access the channel at the same time. As a simplistic example, suppose that time is divided into discrete slots. Okay, with each of the n hosts, there are n hosts attempting to use the channel with the probability p during each slot. Of slots will be linked to the collision. Each of the n hosts transmits with probability p. They are hosts. I don't understand like the thing. A design of broadcast subnet. A design of a broadcast subnet is the capacity wasted when multiple hosts attempt to access the channel at the same time. There's a channel and this broadcasting something, like Twitch is broadcasting something, and it has this when multiple try to at the same time. We click like at the same time. As a simple example, suppose that time is divided into discrete slots. The time is divided into discrete slots with each of the n hosts. Who are the hosts? Me and someone, and maybe someone and someone due to collisions. We agree? Each of the n hosts transmit with the probability p. Yeah, that x number of hosts transmitting in a slot. So if yeah, like x number of people, like slot is like one fraction of a time. Like we clicked in one slot. To the n. Okay, n. If the n is more than 2 or equals to, there's the collision. Collision equals the probability of me joining the session is 1. Like, no. Collision 1 minus p0 minus p1. That no one transmits in a slot. So, I have a probability to transmit in a slot. The probability that I don't transmit is 1 minus p. That is understandable. I understand this. But why in power n? Because there are n people, right? And that means we have to like power it. Because like another person is like 1 minus p as well. So times is, in the end. You know? 2 people, 2, 3 people, 3. Yeah, true. That's, yeah, I like this. I understand this. I understand this. We understand this. By the way, let me. Can I edit my stream here? Network fundamentals. Title and description. probability exactly 1 transmits. So there are n people, and in that n people, I transmitted. Only I transmitted. Right? That I transmitted is probability that I transmit times probability that no one transmits. Like n minus 1, like me, n minus 1, people won't transmit. So n minus 1, this times probability of mine. But why is this n here? Why is this n here, guys? This is the probability that except for me, no one transmits, right? No, no. This is no one transmitting. But if I transmit, there is n minus 1, about my probability. But npyn. In this section, in this section, why, when exactly 1 transmits, there is n times p times 1 minus p in the power of n minus 1 minus 1. When either the 1 transmits. Wait. Why is there n times p? In the case step in understanding binomial probabilities. Okay. Pick that the 1 host transmits. Yeah. Pick one specific host. Let's say we focus on host number 1. For host number 1 to be the only transmitter, host 1 must transmit with the probability of p. Yeah. Yes. So for a specific host, yeah. So any host can be that one. That's what I forgot. That's what I forgot. Yeah, that's what I forgot. Now I understand. Wait, I understand. What are 2 reasons for using layered protocols? Notice one possible disadvantage of using layered protocols. Then leads to breaking up the design problem into smaller, more manageable pieces. And layering means that protocols can be changed without affecting higher or lower ones. Yeah. One possible disadvantage is the performance of a layered system is likely to be worse than a performance monolithic system. Although it is difficult to implement and manage a monolithic system. Okay. The paint of the Specialty Paint Corp, SPC, gets the idea to work with a local beer brewer to produce an invisible beer in the beer can as an anti-litter measure. Us. In the ISO protocol model, physical communication takes place only in the lowest layer, not in every layer. Okay. Yes. ISO protocol. Or is ISO protocol model. Yeah, but physical is only yeah, the physical. Two networks each provide reliable connection-oriented service. One of them offers a reliable byte stream, and the other offers a reliable message stream. Byte stream and message are identical. If so, why is this distinction made? If not, give an example of how they differ. Message stream, like packets, and you know, 12. They are different. In a message stream, the network keeps track of message boundaries. In a byte stream, it does not. For example, suppose a process writes uh, okay, this 120,024 bytes to a connection, and then a little later write another. Yeah, the receiver then does a read for yeah. Basically, the receiver will get two messages of yeah with a byte stream. In the message, the receiver will get two messages. Yeah. Oh, message stream divides to two messages. Okay. Mhm. The receiver. Okay. Okay, what does negotiation mean when discussing network protocols? Give an example. Yeah, so negotiation doesn't happen on the different layers. It happens like on the same level layers. They negotiate which protocols they wanna use. Uh, for example, what transport layer negotiates like, or maybe mm, kinda sketchy, kinda sketchy. I wanted to say I want to say many things now, but I forgot. For example, on what language they want to communicate the message. For example, on the physical layer, they want to use like satellite, or they're gonna use fiber. You know, 13. Let's say negotiation has to do with the getting both sides to agree on some parameters or values to be used during communication. Maximum packet size is one example, but there are many others. Yeah. In figure 119, a service is shown. Us. Figure 119. A service is shown between a service and a protocol. Service provided by layer K plus 1, layer K minus 1. But K provides the service to the layer. It provides a service. Because like this guy asks for something. And this guy does that. This guy asks, this guy does that. I don't know. Z. Service is shown. Are any other service implicit in this figure? If so, where? If not, why not? There is one service shown. Uh, K to layer K plus 1. Another service that must be present is below layer K, namely the service offered to layer K by the underlying layer K minus 1. So yeah, from k minus 1 to k. Yeah, I think here or here. I think here, right? So let's see. The service shown in the service k plus 1. Another service. The service shown is a service offered by layer k to layer k plus 1. Another service that must be present in is below layer k, namely the service offered to layer k by the underlying layer k minus 1. Okay. Okay. And on the other side, I don't know. In some networks, the data link layer handles transmission errors by requesting that the damaged frames be retransmitted. If the probability of a frames being damaged is p, what is the mean number of transmission required to send a frame? Assume that acknowledgements are never lost. If the probability of being damaged is p, if some networks in some of the data link layer handles transmission errors by requiring that the damaged frames be retransmitted, okay, understandable. If the probability of frames being damaged is p, what is the mean number of transmissions required to send a frame? The mean number. Yeah. Mean. There's a model, there's median, there's a mean. Is the mean number. Average? Central of a data set. Yeah. That's mean is just average. I know what mean is. Then with this p. What is the mean number of transmissions required to send a frame? P is plus 1 minus p. 15. 1 over 1 minus p. I don't know. What's a pk of a frame requiring that the k transmissions is a probability transmissions required to send a frame. So the probability p k of a frame requiring exactly k transmissions. So the probability pk k minus attempts failing. Succeeding. 1 minus p. The mean number of transmissions is then just holy shit. So that means that there is a k number, something like even n number that we are gonna send the transmission, right? Requires transmissions like frame requires a number of transmissions, n transmissions, n transmissions. Probability to fail is p. There's gonna be only one case, so when it's transmitted and like whatnot, yeah. So n minus one. Hmm. Let's see. Let's ask. Let's ask. That's GPT because I don't understand that. Then a frame is transmitted. Each transmission succeeds with probability 1 minus p. It fails is damaged with probability p. If it fails, retransmit until success. We want expected mean number of transmissions until the first success. Geometry random variable number of trials until first success. Known result. For geometry distribution, 1 over success probability. What? So easy. Intuition. If p equals 0, no errors. Always send once. Uh, what about this solution? What about this solution? It won't understand. It's so messy. Failing. P k minus 1. To need exactly k transmissions, first k won't fail. Pick him and see. Hmm? 1 over p. Mean expected value. The mean number of transmission is epsilon n equals 1. Expecting number. Uh, I want to understand these symbols. The summation expression. The sequence of terms means so something in K means plug in K, 1, 2, 3, 4. Okay. Okay. For 1 it's 1. Yeah. For 2 to minus 1 it's 2. Yeah. Weighted infinite series, powers of x, x0, x. Okay. Okay. 2, 4, 6, 8, and 10. Okay. One. Don't understand. I don't understand. I don't understand. I don't understand. range like height or time, you can integral mean, okay, equals continuous probability distribution, because you cannot list every single decimal between 0 and 1. Take our standard distribution formula. If you have the probability distribution, okay. I have the event. I have the event. For that event not to happen, the probability is P. This event is done. This event happens X times. Different story. Identify the distribution. The sample is a series of independent trials that continue until the first success and demonstrates. This is a geometric distribution. Defines the probability of success. Yes, we have to learn the distributions from the beginning. Fuck this shit, man. Probability of K transmissions. Expected value. The mean, okay, K times its probability. Using the infinite series property. Okay. I want to understand this formula, man. Alongside this, I figured out that we need to be learning calculus from the beginning. From the beginning. I have some exercises, but it's not heavy, I think, right? Mm, using the infinite series property. Okay, pk minus 1 equals. And when learning and solving these kind of problems, what level of math is required? A minimum level to start solving these problems. In basic algebraic equations, fractions, power like xk, exponents and logs, basic 2x pk, understanding gross dca, basic probability. Dependence multiplication rule. Actually assume this is the really required level of the thermostat problems, discrete probabilities, summations, basic combinatorics. Helpful but not strictly like calculus light level. You don't need full calculus, but it helps. Derivatives used to derive series like this. Basic integrals, sometimes in advanced network queuing, but you can solve 90% of the network textbook. For different, if you go deeper into network research or performance modeling, probability theory, Markov chains, Bayesian processes, stochastic processes, quantum theory, systems be too slow, information theory, entropy channel capacity, K-truth, important mindset. And math is not about heavy math, it's about patterns in randomness. We're reduced to this is the probability of success failure. How often do collisions happen? What is the average number of tries? Real answer is one line. You need basic probability plus algebra plus comfort with summation or notation. You don't need. Yeah, do it. Yeah. Mm-hmm. I understand that. Discrete distributions called model repeated attempts and failures. Learn binomial distribution. Number of successes in n trials. Number of trials until first success. K formulas. Success probability. 1 minus P. Expected value. Be able to compute through output. Find the wasted capacity. Optimize P. Sometimes given. Performance intuition. Advanced beginner. Goal. Understand why networks behave badly under load. Learn. Trade-off. Efficiency versus collisions. Optimal transmission probability. P equals over n 1 over n. Max efficiency equals 37%. You should be able to explain why conjunction happens. Understand why internet uses CSMA CD. Pace. Queuing intuition. Optional but powerful. Delay in real systems. Latency versus through output. Simple query idea arrivals versus service rate. Just love basic idea only. You should be able to explain why delay increases sharply near saturation. Give me practice problems for pace 1, 2 and simulate a real exam with coaching. Like a real exam plus coaching mode. It'll give you a place of practice problems and run a mock exam. Okay, part 1, practice problems. Part 1, 2. Don't rush. Problem 1, basic probability. A horse transmits in a time slot with probability P is okay. What is the probability that transmit? 0.8. Okay. Problem 2, independent events. Two hosts A and B, each transmits with probability P 0.3. What is the probability both transmit? Like probability of that one and probability of that one, like 0.9, 0.09. I mean, no transmission. There are n 4 hosts, each transmits with probability P 0.5. The probability that no one transmits. No one transmits. Same, you know, like times n. Exactly one success, intuition. And that's problem C. What is the probability that exactly one host transmits? And try reasoning before formula. Okay, so so it should be less than 2, right? So if there is a P equals 0.5, we have there is no one, there is no one, there is 1. Okay, so the collision was that 1 minus no one transmitted and 1 transmitted. And when 1 transmits, is that no one else transmits. Right? So anyone can transmit times P times 1 minus P times n minus 1. Yep. So 4 times 2 times 0.5 in 3 is 2 times 0.25 times 0.5, 0.125. This is 0.25. What? Yeah. Okay. Problem 6, value intuition. Wait. Problem 5, geometric intuition. A frame transmission success with probability 0.8. What is the probability if it succeeds on the first try? On the first try. 0.8, I think. 0.8. 0.2 times 0.8. 0.16. Expect value intuition. This was 5. Problem 6 is 5. Stop here. Check answers. As I said. Problem 3. And yeah. Oh, I didn't solve this. I solved this correctly. Yep. 0.8, as I said. 0.16, as I said. Yep. Expected value. P, failure, careful. Success equals failure is this. Okay. So, okay. I am. Timed mini exam. Collision probability problem. Network model. Throw collision mix. Coach, you like think here. Don't jump steps. This is a trick. Part 2. Real exam simulation. Start exam. Collision basics. There are 3 hosts. Each host transmits in a slot with probability. Okay. The probability is that no host transmits. No host transmits. Wait a minute. First one. No host. Not only like no host. 0.8 times 0.8 times 0.8. Okay. 2. If you need it. So it is 0.8. Coaching note. Question 1b. Next step. Now we continue the same scenario. 3 hosts. Okay. What is the probability? Exactly 1 host transmits. One host. This was the one host. As the formula shortcut. collision probability. Now we add and minus 0.384 minus 0.512. Same system. What fraction of slots are successful transmissions? Exam wrap up. Same system. N equals 3, P equals probability equals 0.2. What fraction of slots are successful transmissions? What fraction of slots? When there is no collision. It's successful when there is no collision, right? 1 minus collision. No? Complement. Careful. But be precise. P success equals P minus collision. Oh, and P idle. Okay. P1 transmission. Okay. Okay. When transmits. Okay. Okay. Binomial probability structure. Independence reasoning. Collision modeling. Complement logic. Very important in networking. Increase level. Slotted broadcast system. Setup already careful. A slotted channel has 5 hosts. Each transmits with okay. Okay, hint, minimal. Use either direct logic, choose one host, success, other silent. Yeah. Question 2, harder concept. Slot is wasted, so it's idle. Idle or collision. 3, interpretation. If this system runs for a long time, what fraction of time is actually used for useful transmission? In this system, if this system runs for a long time, what fraction of time is actually used for useful transmissions? Oh, sorry. Different things were provided. Oh my god. Coaching video. Okay, now to important. What is the probability the slot is wasted? Okay. Okay, calculator. There was a P was let me check. Okay, 5 hosts P equals 0.3. So it's idle or collision, right? To determine collision, we need to determine first 1 minus the idle is okay. Let's determine idle. Have n hosts when no one transmits 0.7 in the power of 5. These okay plus 5 times 0.3 0.7 in the power of 4 minus 1 minus this no minus 0.7 the power of 5, and this is the answer. Correct. Question 3. Concept important. In 1 or 2 sentences, what does successful utilization mean in this system? Reply with your explanation. Successful utilization means that slot is not wasted, it is not idle, or neither there is collision. No? It's basic, but it's cited in exam preference. So successful utilization means. Okay. Aloha. System ism topic or real TCP behavior intuition. Just tell me. Let's upgrade each other. Okay, let's upgrade. Let me take a pee. Okay, core idea. What value of P makes the system not efficient? Maximum throughout. No, wait. Let's upgrade. But now we will real into performance thinking. Classic Tatenbaum exam difficulty is where you start thinking like protocol designers. Advanced exam level setup. A slotted system has identical hosts. Each transmitted with the probability P. We define transmission per slot. Okay. Question on correct idea. What value of P? What value of P makes them most efficient? Maximize through output. Okay. Calculus. Let's think conceptually first. If P is very small, is the optimal P closer to 0 or 1 or somewhere in between? Explain briefly. It shouldn't be 0.15, right? Shouldn't be. It should be more inclined to the axis than yeah. But too much axis will mean the collisions. But it's better that there is idle time than the collisions, right? Uh, yeah, this is successful. Collision and yeah. Wait. Collision becomes bigger when transmission. Yeah. Uh, P should be closer to 1. No. What? Somewhere in between. Yeah, small enough to avoid collisions, large enough to avoid idle slots. Okay, we know, we understand. If it's failure, idle slots dominate, yeah. Very large collisions dominate, yes. Medium, best balance. If we continue to increase P, eventually collision pro rate will increase as well. That collision increase. Full explanation. Exam level. As P increases, more transmissions per slot, more hosts try to send. Non-linearly, because multiple hosts choose the same slot more often, collisions grow faster than successful transmissions. Successful transmissions decrease. It becomes rare. Final exam assignment. Okay. See, yeah, as the n number of hosts increases, what must happen to P to keep performance efficient? Explain briefly. As n increases, so if number of slots are increasing, we should balance it out with P increasing as well. I think so. Host. Wait, number of hosts, decrease P. Oh, yes. Yes. The system tries to keep NP constant. Yeah, why? Next level. G, average number of transmission attempts per slot. And the K result is S equals GE in Manchi, where S equals successful through output. Packets per slot. So, slotted Aloha model. Time is divided into slots. Each host transmits with probability P. There are many hosts. Yeah. We define G equals average number of transmission attempts per slot. Okay. So in one slot, there's some average number of transmissions. G. We to K result of understanding as optimal G. Slot Aloha achieves about okay. This number meaning in plain language, explained in terms of channel usage efficiency. Deep intuition, important exam question. Why can't Aloha ever reach 100% efficiency? Average number of transmission attempts per slot. In question 1, if there are n transmitters, n hosts trying to transmit, average should be n over 2. No, n over 2. No. No, 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 no. Okay, 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 okay. Yeah, there's no transmissions. G equals 1. So the peak occurs at G equals 1. G equals 1. What does S? Okay. 30% of slots carry successful transmissions. There's reservation, lower collision. So even in the best case, more than half the channel is inefficient. Why not 100% efficiency? Because transmissions are random. Collisions are unavoidable when multiple users share medium. You cannot perfectly schedule without centralized control. G is 1. I understand that. So next I can take you into CSMA CD, Internet Real World Behavior. CSMA CD. Okay, let's go. Okay, let's go. Are we moving? Okay, internet standard. This theory becomes very real system engineering. Okay, carrier sense, listen before talking. Multiple access, carrier sense, multiple access collision detection. Okay. How much I have been streaming already? 3 hours. Guys, we have to stream on this. Okay. So I think that I will be practicing the more networking, but we have to work on our math as well. We need to work on our this code, you know. So the networks kind of feel a bit harder. Yeah, we have to figure it out. That math, we definitely need math. I think so, but ChatGPT, I don't figure it out math until you need to, right? So let's not do that. Got out while we go. Okay, so we're gonna be doing this. I wanna read this real bad. We're just right here, and there are 25 chapters. Yeah, let's go. I'm gonna be reading this for 1 hour a day. I don't know. I wanna stream, but I don't know what to do. You know, think that on stream we are gonna be just going through flash